Thank you for the invitation. It's there's an introduction. Let me make some number theories objects. That are associated with it. Have Dirichlet coefficients. Coefficients of these functions. Data scientific method in tools. Arithmetic objects in different perspectives. To something. Applying this methodology to the data set, those elliptic curves and the review of. We are focused on the case of the elliptic curves. Something like 2000, about 3 years ago, still it's going on, getting serious.
Just curious, which archive do you post to?
Oh, that's a good. Number theory and then machine learning, statistics.
LFTH, just for the for the flavor. I was curious who you think your audience is. I think. Yeah, okay.
Okay, elliptic curves. What these are? Here is an example. Comes with this label. I mean, if the conductor is how can I say? 496 is the conductor. I will talk about elliptic curve can be written in Weierstrass equation. Is we have this Weierstrass equation of the curve, and the rational points of an elliptic curve is a finitely generated. There is no, and this rank part is rank is interesting. There is no general algorithm to compute the rank, and it is known whether I just know some people that it can be arbitrary filters. Yes, should be found. We don't know. And rank 0, 50% of elliptic same rank. Statistically, have rank 0 and rank 1, and the other ranks are very rare. I mean, statistically, But if you look at the first data set, but it is, and that's true. But the known result is at least 5/8 of elliptic curves over Q have a rank 0 or 1. I think that's the best known result. Question: now, can you apply machine learning to question? The rank is difficult to compute. Can machine learning classify elliptic curves?
I mean, do you assume the Schmidt and Dyer conjecture here or not? You know, I don't this.
No, we don't.
But then it would be easy to compute. Assume.
Easy, but if we assume that from the, you mean the, I think, yeah.
You don't assume.
Yeah, we don't know. But in some sense, we see the BSD conjecture and the validity of the BSD conjecture.
I got to ask a question. I mean, I was confused in the first transparency you said, since there were a few. So for some reason, I would say the Weierstrass equation, you identify y with the derivative of the Weierstrass. I mean, it's a differential equation also for the Weierstrass function. And you, I mean, this what you call the Weierstrass equation is the Tate form.
Weierstrass.
Is that the Tate form? I mean, well, I don't want to be picky, but this doesn't fulfill the Weierstrass equation if we identify y with the derivative. It's not the differential equation for the Weierstrass form, isn't it?
My point is an elliptic curve accumulated in this form. That's my.
Yeah. It does confuse about the word Weierstrass.
Okay,
I said it's a Tate form.
Okay.
It's called the long Weierstrass.
Okay.
We're on the same page.
Yeah.
Elliptic curve is.
Can I just ask about statistics?
Yeah.
So you're giving these statistical things. How many, I mean, do we know? Or is it just a case of because you just obey that, say there's an infinite number, and I just use a computer to generate as many as I possibly? Or is it that you have some notion of a known data set of elliptic curves? And if so, how big is that base?
I don't know the direct numbers, how big is the data set, etc. But so still, it's very difficult to see this fact. So actually, the known data set shows the majority is rank 0, rank 1 or 0. So actually, it's in order to see this, you have to, in order to see this statistical fact, you have to go very further to the data set, and then the known data set actually doesn't show this yet. Okay. And then it's like the percentage is 0. Like 86 or something. It doesn't go down to 0.5. But we believe that this should in the end.
Yeah, I think I'm asking about this sort of asymptotic statistics of it, of whether you're in the asymptotic realm yet.
Yeah,
I think you're telling me you're not, because it's not showing.
Yeah.
Okay.
Yeah.
But regarding the first part of the model A can also be arbitrarily large.
Oh no, the torsion part is known, so there is
okay.
Some disclosure.
And what's the darkness?
But we can find out. Look up the. Okay. Any other questions? Okay. Yeah, we have this question. And then the is how to present an elliptic curve to a machine. That's the first question. So for an elliptic curve of a Q, one may try minimal bias here Weierstrass equation, and I mean the equation we saw. Yeah, because the elliptic curve is defined using the equation, through the equation, then we can use it, we can use the equation. But actually, it was not very successful in recognizing a rank. Actually, Yang and his collaborators did this experiment, the initial stage, and then Weierstrass coefficients could not capture the ranks. I mean, they found out interesting structures in the set of coefficients, but was not very successful in. Then, so it's very, very important how to present arithmetic object to a machine. Sometimes, if you present the arithmetic object in a certain way, then machine learning will be basically useless, or it may not be very successful. So this is one example. But later, I mean, but then how the question is how to present this elliptic curve. Already, we got an idea. So we have to think about this BSD conjecture. Yeah, exactly. It's the natural thing you have to consider. So what does it say? So for each prime P, define this number of points over finite fields FP. So you use the equation P and then count the number of solutions. Then, for example, for this curve, yeah, we have these numbers. And ask is there any relationship between number of points mod P and then the rank? Then we have an idea. If the rank is big and the the size is big, and then the NP must be bigger. Okay, that's the natural expectation. And in the early 96, Sweeney and Dyer used to add Saktu on this campus, calculate this NP and observe this. So indeed, NP, if NP is large, then rank should be larger. BSD conjecture. So then, clearly, from this observation, is related to the rank. So we made elliptic curve using this NP. But as maybe better to consider some normalization. So we define AP by P plus 1 minus NP line, or we may also consider the trace of the Frobenius section. So AP, considering this AP is for the same elliptic curve we saw, now AP coefficients are these. Just calculate this easily for these small primes. Then for a fixed K number, 100 or 1,000, or some small number, an elliptic this sequence. Okay, this is a vector, K-dimensional vector. And of course, we cannot say that this determines the elliptic curve uniquely, because we have to think about the isogenic. But in any case, this were the characterization of the elliptic curves to be presented on a machine. Okay, that's it.
And if this curve is at point of complex multiplication, they grow much slower.
Yeah,
you avoid this point.
If we at this point we just consider everything, but as you said, if you elliptic curve half of the coefficients are 0. Yeah, so we can see immediately, and then actually the machine sees 100%. So, but at this point, we just it's a set up a general thing. Yeah, that's right. And then we consider a set of a set F consisting of elliptic curves. Then we obtain this data set. F is a family of elliptic curves, and then each curve is represented by these AP coefficients. And this is a perfect data set because in like machine learning, we have this basically the k-dimensional back vector. Then we have a certain number of data points. So it's the same in any data set. So we may apply this data set and in particular, using machine learning techniques to the classification problem. So we have this data set and then the classification ranks 0, 1, 2, etc. We may consider this problem. So this, as I said, it is similar to a classification of pictures using machine learning. There is no difference because pictures. What is a picture? To a machine, this is a sequence of numbers. So there is a famous classical problem in machine learning that we classify the handwritten digits, from 0 to 9, and then machine the picture, and then machine will tell this is 0 or 1. But the picture is basically some vector, 256 dimensional vector, and then using from the vector, machine will tell this is 0 or 1 or 2. So it's exactly the same. Okay, so we'll apply machine learning. Let me talk about types of machine learning. And there are three types, basically three types of machine learning. The first type is supervised learning. We train a machine with a known classification labels. We provide labels as well and then train, and then later the machine will predict the new data point if the point is, and then the machine will classify the data. And unsupervised learning, here we do not provide the labels, we just put data points only, and then see if the machine can recognize the patterns where it can cluster the data points according to whatever the categories are. And the third type is a reinforcement learning, where there is a notion of an agent and so an environment. An agent will learn by trial and error. There is a reward, sometimes penalty, and then that's the basic algorithm. So first, let's talk about supervised learning. Then third learnings are logistic regression, support vector machine, and convolutional neural network, random forest, etc. But in our case, logistic regression was enough. So let me talk about logistic regression. I hope that this is not true. Everyone uses logistic regression. Okay, then let me talk about it.
Yes, please.
Okay. So this is a data set. It's a very simple data set. We have capital N many data points, and then it's a binary classification. So the category label is 0 and 1. Then it's one-dimensional vector x, just x value. For example, GRE scores or test scores and admissions to graduate program, graduate school. And the GRE score 272 rejected, 300, etc. Then this is. And question is, now X is a GRE score is 299. Then what is the probability to be accepted? Okay, that's the problem of a logistic regression. So probability. Okay. Then what can we do here? So we are talking about probability. The idea is we have to transform the GRE scores to a probability Yn of admission. So student with this GRE score will be accepted with a probability Yn. Basically, some like a number to a probability. So we need a function from the real line to interval from 0 to 1. And here, usually, we use this logistic sigmoid function. That's the definition, and it converts real line to the interval from 0 to 1. Okay, except this, all the other things are just linear regression. So consider this linear regression. Here, we don't know W1 and B, or it will be determined to be the best, to give you the best fit. And we define this probability using a sigmoid function. So linear regression, and then just apply sigma, then it becomes probability. So it's essentially, logistic regression is nothing but linear regression. So we have data set, scores, we now consider will be like transformed to probability using this process, linear regression, and then sigma. I think we can do this. Okay. Then we assume that the set of scores are independent, different. And we can just multiply the probabilities. So then the likelihood function can be written in this way. This looks strange at first, but it's nothing but if T0 is 1 success, then probability of success. If T0 is 0, then it just picks up the probability of a failure. So it's just nice expression, but the meaning is very simple. And then what's next? We want to obtain the best fit for the given data set. Yeah. And we want to have the best fit. In this context, what does that mean? That means we want to determine this W, the linear regression, so that the given data set may have the maximum likelihood. And then we may follow the data set, the result is the best fit. Okay, that's the problem. Then what can we do? We just maximize this probability P. And clearly, everyone will do, will take the log of this function, obviously, and then maximize this. But usually, the cycle and then maximize something. So they usually put minus sign there, and then they minimize this. And this called the cross entropy error, which it is related to information, some notions in information. So then how can we minimize this? We just take the derivative. And then taking the derivative is not difficult at all. And even though Yn has this sigmoid function, the sigmoid function is the solution to the first order differential equation. So this is easy. Then we use gradient descent, minimize this function. So that's the idea. That's the end of the logistic regression. Basically, this is a linear regression. Then we solution through this gradient descent. Okay, so that's the algorithm. Using gradient descent, we obtain W, these numbers. It converges in 0.0001. Very simple thing. And then if x is 299, plug in the numbers and 0.454 from this regression. And if you look at the table again, yeah, this seems to be reasonable. 272 was rejected, but 331 was accepted, etc. And 299, it has probability 0.45. And if GRE score is 277, probability is very low, 0.012, and 310. So yeah, this is this regression. And people may not be interested in the probability at all, so they want to ask either I'll be accepted or rejected. Then what we do, we just put some threshold like 0.5, then make the machine make the predictions. So with this score, you will be rejected. Yes. So that's the usual practice in machine learning. There should be some threshold. Okay, now, but there was a simple generalization would be like this. So, instead of just one feature, there may be k features. So like a GRE score and then GPA, etc. Or in like classifying pictures, these are 256 pixels. And then TN can be rejected or accepted. Or in like a handwritten digit problem, can be from 0 to 9. That's the generalization. And then sigmoid function is now really generalizing this through this softmax function. The total sum is 1, as you can see, and it plays the role of the sigmoid function in this case. If there are more than 2 categories, usually you and the linear regression function is this probability, and then just take the log and put minus sign, and that's the error function. And then we want to minimize this E of U. Then you can take the derivative. It's now more complicated, but still we can do the multivariate. So take the derivative. And then apply the gradient descent, and that's the logistic regression. So this simple algorithm is actually very powerful. If you do some experiments, then at first you'd be very surprised. Actually, I was very surprised because using this very simple algorithm, can recognize handwritten digits with the accuracy more than 90%. Moreover, a neural network is or may be considered as multi-layers of logistic regressions. The neural network sounds very complicated, but actually it is complicated. But it's complicated because there are many parameters. But the basic idea is just applying this logistic regression. And yeah, and then yeah, that's a neural network.
And then what happened to the accuracy if you have multiple layers?
Can you repeat that?
What happens then to this accuracy of 90%?
I mean, this handwritten the data set is very classical. So many people have been applying specific like machine learning tools. So the convolutional neural network works very well, and the accuracy is 99.8. So it's kind of perfect. It may probably it's better than human eyes. If you apply the so-called convolutional neural network.
Even before convolution, multi-layer, I think 3-layer will take you up to 98%.
Yeah, even.
Pretty like that.
Yeah. It's even like a 1 layer. Logistic regression is just 1 layer, and it's more than 90%. Actually, if you think about it, then it's amazing. So because the machine doesn't know anything like the connectedness or topology or the graph theory, it doesn't have anything. It just have 200 dimensional vector in this algorithm, and then it determines the handwritten digits like this actress. And the 3 layers set right 98%. So once you want to see a perfect result, then CNN, then it's almost. So if you see the picture, 6 or 0. All the things are actually very convenient, 1 and 7. But
So is the accuracy sensitive to the choice of this probability function, like this Yang-Hui function or something like that?
yes, yeah. So
Would one choose another kind of probability function instead of?
I have not tried, but some people use hypertension. That may be other choice, but I'm not sure. But sigmoid is default kind of default choice. So yeah, of course it will be sensitive. But how much it is sensitive, I don't know.
The neural networks, you have the standard thing is called ReLU, which is
Yeah, really. Yeah.
activation function. There are always they have to be a nonlinear function. After that, the difference only matters by 1% on the finals.
So in the neural network in the middle, we usually use this. Okay. Back to elliptic curves. Then where can you find the list of elliptic curves? Okay, so we want to have an idea how to apply the machine learning to elliptic curves, but we have to make a data set. So the great resource is this LMFDB, the L function comes data. So if you have not visited this website, then strongly suggest that you visit this. So you visit this website, and then here is the item or the section of elliptic curves over Q. And then you see a list of curves. Then you can download the data set.
Available as a CSV file.
Oh yeah. I mean, I don't know the format, but definitely you can convert it to CSV.
I don't want to spend my time converting.
Yeah, it's good.
There are a few options. There's Sage, Pari, and a few you can just click down on. It's not too bad. About 10 million curves on the order of 10 million.
That's what I was going to say. That's my first. It says 10 million curves.
On the order of 5 million over Q, 10 million over.
Yeah, for initial experiments, it's very easy.
But if they assemble this curve, they have a bias of the design. I mean, how do they select the curves?
Oh yeah, that's a good question. So, yeah, I mean, actually is the order is according to the conductor. Yeah, that.
And it's basically low conductor.
Yeah, low conductor. The conductors can be like a 10 to the 30, for example.
You got to tell me what conductor is.
Yes. Yeah, okay. So it will show probably the second half of this slide. But we can form various data sets. If you look at the data set, and you can choose a conductor. So for example, you can choose a conductor range from like 1,000 to 2,000, for example. And then you can search, and also you can specify rank or many other things. So what I'm saying is that we can form various data sets. And then, in LMFDB, the elliptic curves are ordered by their conductors. Somehow, people who made this LMFDB saw conductors should be the labels. Cremona made a big database for elliptic curves. He used the conductor. So then, what is a conductor? Elliptic is a bad reduction at P if the reduction of E out of P is a singular. P is a singularity, then that's a bad reduction. Or equivalently, if the P divides it's a discriminant. And then the conductor of E has this form. So the bad reduction, according to the type of singularity, you determine the exponent. Okay, and then you so it's basically it measures how complex the elliptic curve is in some sense. In some sense, so it measures the size of the elliptic curve. The size is in some sense. But there are other measurements, like there are heights. Also, there may be other things, discriminants, but LMFDB uses conductors. So we will also use
Tetas, sorry, tetas you get. Or you get the tetas.
Tetas.
The
Oh,
Oh, but this is maybe I should. I'm not at.
EP, exponent. So if the singularity is the nodal singularity, then this exponent is 1, and then if this is the cuspidal singularity, then the exponent is 2. But if P is
So basically the degeneration of this.
okay. Yeah, it really looks like a theta, but
Maybe 90%.
We need a neural network.
It's listen noise. Let's get that class.
But I typed it, so I knew. Okay, so as a first example, make a data set using F consisting of 16,000 elliptic curves of rank 0 and 16,000 of elliptic curves of rank 1. And the conductor range is from 1 to 10 to the 4th, 10,000. And then we'll choose K to be 300. Okay, then we have a nice data set. And we'll do this binary classification if the rank is 0 or 1. Then, because we know the logistic regression, we'll apply logistic regression to this classification problem. Okay. Then, how and what do you expect as an accuracy? But of course, we have to train the machine. So we will randomly choose 80% for training and the remaining 20% for test. Or we can choose any percentage. If it is reasonable, we can choose 50 for training and 50 for test. This the result I will show you. We did this. But this 80 and 20 are not positive.
How much time does it take now to train a machine?
It takes like probably 20 seconds. It's very small, relatively small, and these days on my laptop, and the laptops are very powerful. Yeah, so I think at most 30 seconds. And the accuracy was Actually, if you know well about these and then energy rank and then how to, then it's not a big surprise.
It's accuracy on class prediction, on rank prediction.
Rank
prediction.
And there was, okay, so maybe I lost it, but the AK, I mean, before that, in the Tate or Weierstrass form, you had this A.
Those are, I'm sorry,
that's-
those are different. Yeah.
So,
This is
now
the AP and then those are.
so the A's are, so the AKs are what? against?
The A.
This is a
AP. So let me see if I didn't mess up the. Yeah, exactly. AP1, 2 basically, then 3, 5, and A 300. I forgot. So 300th prime, whatever. Then. Yeah.
But you reduce the curve over set P, right? I mean, so you consider the curve over the finite number.
Oh,
Set.
okay. When you calculate, I mean, in the beginning it's over Q or over Q.
But later you choose.
No, we just when you calculate a P, we consider we reduce the curve of mod P. Otherwise,
Yeah, mod P.
yeah, mod P. For AP. Yeah.
But then essentially like 300 coefficients predict the prime.
All right.
And doing something like the bias class coefficients. How well does that do?
The Weierstrass coefficients they had
Coefficients,
like
sorry.
is it 5 or 6?
Okay.
5 coefficients, and then you can do the same. And then the Yang's result is so that it doesn't recognize lengths.
Okay.
So you're saying basically you just look at the prime AP because it's a Hecker eigenform. And
Yeah.
it's like-
And so we have all the products. So, of course, we can consider other like other AN coefficients, but this was enough.
This determines it.
Yeah. Okay, any other question? Okay, then. Yeah, the more precisely, these are the results. The 99% appears here. Actually, if we use only 100 coefficients, and the precision goes down a little bit. Then, if the conductor range is bigger, then we need more AP coefficients to see better accuracy. It's kind of reasonable. It's more the big curves. You need to feed more AP coefficients. Even we train with these conductor with the elliptic curves of this conductor range, and then we test the machine with these conductor range, but still it's somehow there's a high precision.
I mean, I'm still confused. I mean, if you fix the N,
Yeah.
then you know it's a model, a Hecker eigenform, gamma not N.
I'm sorry, this N is not a conductor. So yes,
No,
because
but if you fix the N, isn't that the coefficients, since a finitely generated ring, that the coefficients are determined by very few. Maybe the ring is n-dimensional, so they're actually determined by 10.
do you know the exact number? So I mean, actually, we need number theorists that we only need log of this number. And from the experience, I don't know if there is any proof. So actually, 300 is a lot.
Yeah, so
Yeah,
it's
it's
mostly would determine function.
Yeah.
So can you just understand, so the input that you're putting in, not in terms of the training set, but in terms of the dimensionality, what's the dimension of the input vector?
Oh, here, of course, we 300.
300.
Yeah, but he's pointing out that this is we're already
Some redundancy within that.
Yeah.
Yeah, which you don't mean.
So that's the reason, part of the reason that we are seeing this high accuracy. That's right. So we are, I'm not claiming anything to break through, but we are seeing the same thing from different perspectives. So if we know other things, then of course this is not a surprise. This high accuracy of 99% is not a surprise. But still, this data scientific methods works. And then it provides us a different way to see the same thing. If you know the field conjecture, if you know dimensionality of the modular forms, etc., then there's nothing here. But again, my point is, it's a new method, new way, and they apply this method to other things, new. Yeah, that's the point. And then here, confidence is calculated by the user confidence for binary classification. And then even we can do the classification of elliptic curves with the rank 0, 1, and 2. Then again, we get high precisions, high confidence. So actually, this determining, distinguishing rank 1 curves and rank 2 curves is almost perfect. And here we used this many, so we have used many coefficients. And then this is a three-way classification still, the precision is nice. Okay, then we have to see what's going on here. Because just saying we got high accuracy, then then that's not enough for us mathematicians and mathematical physicists. That's not enough. But then what's going on here? So why do we get these high accuracies? And can we see what machine sees? That's the next. But thankfully, logistic regression is very interpretable, meaning that we can really see what machine sees. But in contrast, deep neural networks are difficult, but logistic regression we can understand. So let us think about this. We're distinguishing rank 1 or 0 or 1 curves from the curves with a rank greater than or equal to 2. And here, 300 were many, but now we just use 10 coefficients. Okay, the first 10 coefficients only. Then we choose 3,400 curves of each class from conductor range from 10,000 to 28,000. Then logistic regression gives us the accuracy of 0.95. And now the number of coefficients are very small, only 10. Then logistic regression is very interpretable. So let's see what happens. Then if you remember the algorithm, it's the linear regression. Okay. So linear regression gives us this slopes and the bias, like kind of a bias. These are given by these numbers exactly. So we know we're seeing over 11 numbers, 10-dimensional and then bias. So just to define this function using the sigmoid function basically. So we are following the algorithm of logistic regression. There's nothing, it's just simply just recover logistic regression and the coefficients are can be written down in this way. Then now consider this curve. So this curve have a rank greater than 2 or equal to 2 or less than or equal to 1. That's the question. And we calculate 10 AP coefficients, and then put the result AP coefficients into the function the classifier. R is a classifier, and then probability is 0.00011 to be a curve of rank greater than or equal to 2. So basically, we are all, which is certainly, almost certainly, has rank 0 or 1. Indeed, the rank is 1. Okay, and consider this curve. And then do the same, and now probability is 0.97. So which means almost certainly this must have a rank 2 or bigger. Then indeed it has a rank 2. So if you consider this, then as you can see, what do you see? The coefficients are very negative. And then first two are very significant, but later the contributions are small. So meaning that first few AP coefficients affect the rank greatly. Okay, that's the conclusion. And then, yeah. So indeed, if you see this, the rank 1 curve has many positives, but the rank 2 curve has generally, all of them are, there's one positive number, but generally it's negative, meaning that it has more rational points, not P. And then there is a consistent with the ESD conjecturally, but similar Dyer observed. So we are seeing that everything is comparable, and then now we understand. So when you have a high accuracy, we should not stop there. If we stop there, then it's just mystery, and then the machine sees something, but we don't see anything. But if we can interpret the machine learning, we may see what's going on, and then hopefully we can find out something new, because it may provide us new perspectives. But here, of course, in this example, you're seeing basically what BSD conjecture says, but it's still interesting.
But how often does it happen that you can interpret what the machine says?
The people are
Depends on the problem.
yeah, depending on the problem, and also the machine learning experts are really trying hard to like to make it better. I mean, make the interpretability better. That's like a whole branch of machine learning. I think yeah, there are many institutions are investing a lot of resources to develop interpretable machine learning. That's very important, because we have this amazing AI, open ChatGPT, open AI and ChatGPT, but we really understand what's going on inside the large language model. And that's what. So, but logistic regression was very simple, and then was very possible.
One layer.
It's one layer.
One layer.
Yeah, one layer you can always do it because analytic. You break it down.
But when you get 10 layers, is it?
When you get 2 actually. There's a big gap between 1 and 2. There's not much of a gap between 2 and 3. By the time you've gone to the key point is the endpoint is that nonlinear function. Most honest. And then you stop there, so far. If you now feed into the next layer of the nonlinear function, you're already then lost it because
Yeah.
the nonlinearity goes through. So then it's like you do with a highly interacting system. You can't do that with n bodies. I mean, I would say one thing, sorry.
Oh yeah.
The one place where you can interpret it in a genuine neural network is exactly do the physics trick. You take the large end of it. So if you have the width of the neural network go to infinity, that is actually analytically solvable again. And you get something called the neural tangent kernel, becomes what's called the Gaussian process. And that is again the physics story of you can do There's one where you can do infinity. And it's the stuff when you've got 100, say, which is what happens that you can't solve.
But
So
in
people
this,
have the neural networks with infinite.
in this limit, everything improves.
No, no. And that's because people imagine that, but the point is, the larger the number of neurons, the harder it is to train. So training capability goes down because you've got an infinite number of things that you've got to teach in that limit. So there's actually a sweet spot when you're designing the network between the number of neurons in terms of how easy it is to train versus how expressible it is.
Mhm.
And this is all a non-linear when you have this problem.
Yeah, that's right. So it's a big problem. But yeah, in our case, it was, and then, yeah. I'm trying to make it basic. So here is another basic thing, PCA. So it's a principal component analysis. The motivation is, can you see any pictures? Because something is going on, but if possible, we want to see some pictures. So our data points live in a high dimensional space. In the previous example, it was a 10-dimensional, but usually we have like a 300 dimension, 500 dimension. So in higher dimensions, the data set becomes very sparse, and our geometry intuition can fail. And severe difficulties that can arise in spaces in high dimensions are usually called the curse of dimensionality. That's the usual term. Frequently dimensionality reduction, basically 2-dimension or 3-dimension, so that we may see the pictures. Is very helpful. And PCA is the common method. It's a method in unsupervised learning. It produces some picture in being unsupervised. So let me go over the PCA. Give it just 2 or 3 slides. So we do that quickly. So here is a data set, D-dimensional space. So for example, this is a 2-dimensional space. D is 2. And then which direction represents the data set best? And of course, everyone will say that we have to look at the data set along this direction, or project data set along to that axis. So that's the idea. So project the data set onto a subspace of dimension n is typically 2 or 3, such that the variance is maximized, and we'll see the structure more clearly. And that's the principal component analysis. Okay, then let's do that. It's an easy calculation. This is the mean average of data points. And U is a unit vector, will give us the direction. And then the U coordinates can be calculated, and then the mean is this. Because we'll have to calculate the variance, we first calculate the mean. And then the variance is literally this, right? And then you just do some manipulation, and then we get this. Here, that's the variance. And then here S is this symmetric matrix. Then we have to maximize this quantity. U is this unit vector, so we have this constraints. Then this is just a problem of Lagrange multiplier. So do the take the derivatives, gradient, and then the Lagrange multiplier gives us this, and it's exactly finding out the eigenvalues and eigenvectors of a matrix S. Matrix X is a covariance matrix. So basically that's PCA, and the variance is now calculated by this, and then it's I comes the direction, and then Q is the variance. Remember that we wanted to maximize the variance. So that means we want to find out the largest eigenvalue. So PCA, finding out m eigenvectors of the covariance matrix S, and then we just order the eigenvalues from the largest one to the smallest one and take the first n. Then it will give us directions. Okay, that's PCA. Back to it. Then we had like 300.
Because I think when you're determining whether a member of the data set is in the model, then you actually want to look at the directions that minimize. Right? Because on that line, if you go along the line, it doesn't tell you whether you're in the model or not when you're going along the line. The thing that tells you whether you're in the model or not is the orthogonal direction where the variance is minimal. So,
okay. Yeah, another. Okay, thank you.
yeah.
Okay, so back to elliptic curves, and then here we want to maximize the variance so that we see the separation, and we apply this, and then obtain this picture. So this is a picture from data set of elliptic curves with a rank 0 or 1, and conductor range is there. And then blue corresponds to blue points are curves with a rank 0, and red points are curves with a 1. And then
So the conductor is plotted there.
From 7,500 to 10,000.
But in which direction?
Here it's hidden, of course. I mean, that's the data set.
But then,
And then
the blue points are the rank 1 and the
rank 0.
Okay, and then the axis they can be.
There'll be the PCA direction.
Yeah, PCA.
Which you won't know what they are because there'll be a linear recombination of the directions that link the data set.
Okay.
That's
Those
right.
in such that they maximize variance.
Yeah.
So you can get separability between the different routes.
Exactly.
Yes.
So x-axis is a PC1, the first principal component for that direction. So it maximizes the variance. And clearly that direction separates rank 0 from rank 1. Now we see picture. Now we understand the logistic regression, which is a linear model. So it does the same thing. The the logistic regression basically separates and then gives us this line. Okay. And then the y, we see the y get y-axis. Clearly blues and blue points and red points are separated. Then they are clustering together. So yeah, it's very helpful to see this kind of picture.
And the thing is, from your logistic regression, the dimensionality was much greater than 2. Because you saw the value of those things were there. So because you might look at that and go, it's actually not very separable in the boundary, but that's because you projected too far down.
Yeah, that's right. So logistic regression keeps a 300 dimensional space and then get some hyperplane, but here it's a 2-dimensional projection. But still, yeah, we see why the logistic regression works well, and we see clear separation. It's projection. And then the same. So we remember that the machine could separate rank 1 from rank 2 very easily, with a high accuracy like a 0.99. Now we see the reason here. There is a gap almost like here. Yeah. Okay. So again, this is PC1, x-axis, y is a PC2, second principal component.
But you're saying it's a reason. Wouldn't I say it's a refinement of the statement that you can separate them easily?
It becomes philosophical at this point. I mean, it's doing what it's doing. What you want to call it. You know.
Yeah, but yeah, the picture shows us, some difference. Okay. It was a PCA. Then, so PCA is highly interpretable because it's basically linear algebra. We can see all the weights. So, from the previous, what is this? So rank 1 and rank 2. Rank 0 and rank 1. And then if we do PCA, now the first component, not component, but x-axis is in AP where x-axis represents P, and then y represents the weight of the first PCA direction. Then 0 is here. Okay. Okay, then good. So we are seeing all the components of the direction. But something is interesting. What is interesting? Oh, yeah, that's right. Exactly. It is intriguing that the weights are oscillating. So we saw that the first few primes are important, but later the importance is changing, and then it is oscillating. So it was like a precursor of something very interesting. So that's the next topic. The murmurations. So what is a murmuration? I didn't know the word. So Yang
Stallings.
Oh, it's stallings. Yang taught me what this is.
That's my only contribution to this part.
Remains he won the Nobel Prize for studying the murmuration of Stallings.
Yeah, I mean, you will see it was something interesting. And then I Googled the murmuration and then found out this picture. This is the murmuration of stallings. So here, the important thing is we fix prime P. It's the fixed prime P, and then it's kind of a vertical thing. P goes as okay. Anyway, so fixed prime P. And then we'll take average of AP for a set of elliptic curves. Okay, more formally, we're considering this function. So n fixes the prime. Again, n is the fixed prime, gives us the fixed prime, and then just average it. Elliptic curves are from this set. Here, n1 and n2 are conductors. So that gives us the conductor region. The average, so we divide it by the number of elliptic curves. And then we plot f0n and f1n. Okay, and then actually Alexei Pastnyakov is an undergraduate student, did this first. I gave him some data set and he did this first because he actually didn't know about elliptic curves. So what he did was just taking the average. And then he showed me this picture. And I was very surprised because I've never seen this kind of picture in any textbook or in any paper. So here again, blue dots represent the rank 0, and then red dots represent rank 1. And then these are averages, not individual curves. So then let's think about the meaning of this. The first behavior is not a separation of rank 0 and rank. He says, PSD says, it should be separated. Okay? But oscillation is very surprising. Why is that? The general philosophy of a PSD is rank 1 must have more number of larger number of rational points. So it should be very negative like this. And then rank 0, fewer rational points. So AP must be bigger because AP is the number of points. That part is not surprising, but the surprising thing is they're oscillating. So it violates the first behavior. Why?
Can I ask another thing? Did you try it with 3 dimensions? Because where you get overlap, you can see you're not separable, but you are separable. So it would be much more likely if this was actually a double helix.
But what do you mean by the 3-dimensional? It's prime.
You've got two PCA directions.
No, it's not PCA.
It's not PCA anymore.
No, not anymore. It's simply the average of APs. It's not PCA.
Yeah.
Oh, I see.
It's not PCA. So this is it. The one direction. This is, and then prime index, and then this is the average. Don't just
Yeah, okay.
and then again the first behavior, okay, BSD, and then the number of rational points multiply. But why are we seeing this oscillation? So that was very surprising, and I showed this to other number theorists, and all of them were surprised. And then no explanation. And
So
then
the average is the coefficients,
average of
the standard deviations,
understand
the standard deviations
debate.
are enough, like
We actually
they can be separated, at least in those regions where they simply touch each other.
the second moment was calculated, but second moment gives us basically nothing. Why is that? The second moment gives us nothing. If you consider the Socrates conjecture, then after some normalization, the second moment should be like a fixed number. It should converge to a certain number. So second moment can be calculated, but basically it is like a constant, some known number. So we understand the behavior for the second moment. But third moment gives us something similar. It should give us something similar. And then rank 0 and rank symmetric. Not really. Anyway.
So is this stable if you change the range of?
Okay, that's probably next slide. So is this a general phenomenon? So first, we do the same for rank 0 and rank 2, and then basically the same behavior, because the behavior should be different. There's rank 2. And there should be separation. What I mean is separation. The rank 2 must have more rational points, not P, generally. But the oscillation seems to be similar. Now, how does this exactly? That's the question. So, how does this oscillation change as the conductor range changes? So, we'll consider this geometric interval. And then do the same. But here, because rank 0 and rank 2 had a similar oscillation, so we'll separate rank like an even rank case from odd rank case. Or if you are familiar with the elliptic curves, these are basically root numbers. Root number 1 and -1, but I'm using 1 and 0. But in any case. And then we sketch the graphs. Actually, the graphs were produced by Andrew Sutherland. So N is from 13, 14, 15, 16, 17. And what kind of picture do you expect? So these 1, 2, 3, 4, 5 graphs are from totally different I mean the separate, they're totally different data sets. Here, different means they have no intersection. But somehow, the pictures are similar, like scale invariant. But here the point
Is there
is
difference?
The horizontal axes are different.
okay. Scale invariant. That means this was 8,000, and then this was 16,000, and etc. This 32,000. It should be scaled.
But could that be, so to say, what I said, that maybe that you don't learn if the conductor is not so high, you don't learn from the additional coefficients actually, because they are all determined by the fact that it's Hecker eigen. Could that be explaining that? I don't know.
So here, no. So in order to learn the next, I see. So you mean the first coefficients were basically produced the later coefficients. In principle, yes, but still, yeah, I don't think we can. I don't know how to argue to make this oscillation.
So the periods are sort of doubling. I mean, the wavelength is
Yes, it's
doubling. So what is it that's, as you go down, these are from the top to the bottom, what is it that's changing?
everything is scaled, but this seems to be. I mean, this is like a wild guess. It was about square root of n times pi over 2 or something like that. Yeah. So if you just if you look at,
I'm sure that's Yang's contribution.
Did you have skill that they
Multiples of pi on your team.
number theories love squares of pi.
everyone likes pi.
Everyone likes pi, yeah. Especially the,
And so
it's fascinating.
yeah, so this was interesting. Okay, so this is from elliptic curves. But what if we order elliptic curves using height? So height is just from this Weierstrass equation. Yeah, use this.
How it's the Weierstrass?
Yeah, I mean, in any case, yeah, Weierstrass equation. And then do the same with the height, then yeah, basically do the same, but not conductors, but height. And
Can I interrupt? I mean, you are a numbers theoretician. Now you have made an observation which is sort of interesting. So what would you do now as a number theoretician?
We have to prove it. I mean, we have to prove the phenomenon and understand during the proof.
But do you have any idea of the strategy?
So yeah, we'll talk about it. Okay, at the last one. So height, yeah, don't just what happened. So it's noise. The height is not a good measurement for this. It should be a conductance.
Because it's not in the Birch-Schwinnert diet. Isn't that surprising?
Yeah. So yeah, height don't give us the picture. And then the enumeration occur only for elliptic curves. Here, what I mean is we immediately remember this modularity theorem. So the elliptic curve is essentially a weight modular form. So if we have an elliptic curve, then there is a weight modular form, and then conductor becomes the level of this group. Then the AP coefficients are exactly the same. The F has either Fourier coefficients, and then the elliptic curve has this AP coefficients or the trace of the Frobenius action, but it's the same. It's as you know, this is a big theorem, and Andrew Weiss proved it, and gave us proof of the Fermat's last theorem. So we were seeing way two modular forms, but elliptic curve is a way two modular form. But there are modular forms of the different weights, of course. So does the enumeration occur with other modular forms? Is a natural question. So everyone knows modular forms. We skip. So just remember that there is in general, there is a Dirichlet character or this multiplier system, right? And then modular form has this Fourier expansion. There's an example. If you have this elliptic curve, then you just count the conductor is now that 496, and then AP coefficients can be calculated as from the Euler product. This way, then yeah, we have a weight modular form of level 496. Weight 4 modular form of here, this is just an example. Weight 4 modular form of level 5 with the trigger character. One example is this. And then weight 4 modular form of level 7 with a chi such that it's not trigger character anymore. Then you may worry that you will get not integers. Indeed, we have these algebraic integers. But that's okay, because if we take the trace of f, the sum of all Galois conjugates of f, then we get integers. So we'll take an average, which means we'll take what sum of all these Galois conjugates. So it's okay, we'll get integers, not algebraic integers. So we can produce the same pictures. Basically, it's according to the Galois orbit size, and then again, and here we have to talk about rank using analytic rank, not algebraic rank anymore, because it's not an elliptic curve. And if we do the same, basically do the same, but here the Galois orbit size will change. And then we are only considering new forms. We want to see only primitive things, not redundant things. And this is a plot. Still, there is an oscillation, or it's wave 4 modular forms. If we add them, this is of all Galois orbits, then actually the picture becomes clearer. And do the same for weight. What was it? This was weight 2 still. We are adding not only Galois orbit size 1, Galois orbit size 1 is elliptic curve, but now we are seeing different Galois orbit size. Weight 2. So this was an elliptic curve. Okay, but we have other thing.
Sorry, in the last one there is no crossing.
That's right, no crossing. Or if there is if we have magnify this and then I don't know, let me see. Yeah, there is no cross. And now this is a wave 4. The fractal normalization, we divide it by the normalization is actually important. And the same basically, same means we still see oscillation. The picture is sparse because the number of data points is now becoming small. I mean the known data set, the available data set is less extensive. Again, the normalization is important. Yeah, these pictures are produced by Andrew Sutherland. So as you can see, this is a general phenomenon among modular forms. But the elliptic curve was a genus 1 curve. What about genus 2 curves?
So if you would not just focus on the new forms, but to also do all the forms,
then the picture becomes blurry.
that I believe, because then you basically don't distinguish, so to say, the factorability of the end.
Yeah. Genus 2 curves. Okay, here we can play the same game. Then the conclusion is we observe a similar murmuration. I will show you the picture. But here we only consider generic curves, generic genus 2 curves. That means the subtotal with USP4. Then we get the average the same way. And this is the picture. The picture is obviously different, but the oscillation is true, and then scale invariance is also true. Okay, then clearly this is a general phenomenon. And actually, Lina announced the proof for murmuration of the set of all weight modular forms. She is a PhD student at Princeton. Her advisor is Peter Sanak. And her proof uses a trace formula. Okay. So, but downside is that she has to use all the forms, trace, because of trace formula has all the modular forms. But elliptic curve is the set of elliptic curves is only like a make it a part of it. So it's not the proof for the elliptic curve case. If we consider all the modular forms, then we can use the trace formula, and then she can produce the graph correctly. But it's not
the
available.
idea of this proof. You know the idea of this proof.
The trace formula is basically what we want, because one side it takes the sum of all AP coefficients, and then the other side it has Horowitz. The generating function of the class numbers, which is the ZBS study. That's the other side. So we can analyze the other side. That's well-known some function modular form. So yeah, so that was her proof. But of course, the details are technical, so she's just still writing. Probably that can be her thesis. And murmurations of Dirichlet characters has been established by me, and then Tom Oliver, and then Alexei Pasniakov. Because this case should be simpler. So GL1 case, then we have these pictures. Yeah. It's not proven. This is proven. And then Andrew Sutherland maintains a web page for murmurations. So he worked very hard. So he produced all these things. So for example, elliptic curves. Then the conductor ranges are increasing, and then see this. So you can visit this website and then see. One more. Yeah, so if we consider everything. Probably here there was no crossing, but later there is a crossing. Okay, and then what's next? We are almost done. There was a hot topics workshop at ISOM on murmurations in arithmetics. So Yang and Ang and Tom, we organized a workshop at ISOM. So people came, and then we discussed the meaning of this murmuration and possible proofs. Let me make a summary. The arithmetic objects can be studied through data scientific methods. Okay. Then we may obtain new perspectives of arithmetic objects, even though we find something already known. This gives us new perspectives. Then we may discover new phenomena reveal hidden structures. I hope that my talk gave a reason. Okay, thank you.
Any questions?
There were lots to it.
Yeah, there were.
We should ask whether the online participants have any questions, if you could just.
Oh. No one asked any.
Alright.
Yeah, no one asked. No one participated online.
There were a few participants.
There were at the beginning.
Okay.
All right, well. there are no
Well, I know
questions.
many questions, but we can maybe discuss.
Yeah.
Yeah. Well, thanks very much.